To understand how some data vectors, such as signals or images, could be represented with the help of other vectors, we need to learn about span and basis. I want to remind you that linear combination of n vectors, where each vector has m components, is just alpha 1 multiplied by v1 plus alpha 2 multiplied by v2, and so on until you get to alpha n multiplied by vn. Each one of those is just some constant coefficient or weight of the vector in that linear combination of vectors. The set of all linear combinations, all possible combinations, is denoted by span of v1 to vn. And it's called linear span of those vectors in Rm. Let's take a few examples. For example, span of the vector 1, 2 is just all possible linear combinations of that vector, which is vectors alpha multiplied by 1 and alpha multiplied by 2. So it's the vector alpha and twice alpha for all alpha belongs to, for example, real numbers, or it could be also complex numbers, but it doesn't matter. So all of the vectors, which is 1, 2, 2, 4, 8, 16, and so on, all of those vectors belong to span of the vector 1, 2, because all of them are proportional to that vector. Now, span of two vectors, 1, 2, and say 3, 4, is essentially all of the plane. So it's all possible pairs of numbers. So any pair of numbers could be written as combination of those two vectors. Because you can write this vector as weighted sum. This is called basis of the R2. Let's pick some random vector. Let's say you want to write vector -1 and 0 as alpha 1 multiplied by the first vector plus alpha 2 multiplied by the second vector. You need to find such alpha 1 and alpha 2 that this will be equality. So let's simplify that a little bit. So it's alpha 1 plus 3 alpha 2. And then you have twice alpha 1 plus 4 alpha 2. From here you have system of equations. First equation is alpha 1 plus 3 alpha 2 equals -1, and twice alpha 1 plus 4 alpha 2 equals 0. So from the second equation you get alpha 1 equals minus twice alpha 2. Now let's put that thing in the first equation, and we'll get minus twice alpha 2 plus 3 alpha 2, which is also equals alpha 2 equals -1. And from here alpha 1 equals 2. Now let's put those numbers back. So instead of alpha 1 and alpha 2, I'll put their numbers. And those numbers will be twice multiplied by the first vector minus 1 multiplied by the second vector. And you can check that this will give me that kind of vector. Unfortunately, this is not always working. For some set of vectors in Rm, we span the entire Rm. And for some others, we are not spanning the entire Rm. So what is going on here? So you have the vectors which span uniquely the entire space Rm. Those are called bases of the Rm. Now, not all vectors are uniquely spanning Rm. And you have also the word uniquely here, which is very important. This means that only unique combination of components alpha 1, alpha 2, alpha 3, and so on will give you specific vector in Rm, which means you don't have multiple solutions to that system of equations. You have only unique solution to that system of equations that we solved in the previous slide. Now, we have important theorem here. This theorem states that m linearly independent vectors are the basis of Rm. Which means if you're taking m vectors which are linearly independent, then they will definitely span the entire Rm space. Pay attention to something very important. Less than m vectors cannot span the entire Rm. So no matter which vectors you choose, if your number of vectors is less than the number of dimensions of the space, like if you're choosing just one vector to span two-dimensional space, you cannot do that. Two-dimensional space should be spanned only by two vectors. More than that, if you're using more than m vectors, it could span the entire space, but it will not be unique, which means you will have some linearly dependent vectors if you have more than m vectors in m-dimensional space. This means that the basis of Rm should have exactly m vectors. So if you have vectors of dimension 2, you need exactly 2 vectors to span two-dimensional space. And those vectors should be linearly independent. If you have, for example, space of size 10, then you need 10 vectors to span that space. Now I will describe the algorithm of eigenfaces. The eigenfaces algorithm was used in face recognition, compression, and more generally in data reduction in images. There is a given set of aligned face images, and you can see example of that kind of set here on that page. So the middle point in all of those images is aligned in all of those sub-images. And for example, in that case, the tip of the nose is the same, has the same coordinate in every single image here compared to the origin point here, which is a corner point. Now you give me a new image like that, which is not part of the database, but it's of kind of similar type, and I want to represent that image as a weighted sum of the other images which are already in the database. This will give me the opportunity to describe it only with a few numbers, which are the weights of my linear combination, and not all of the pixels where you have tons of the pixels to describe. More than that, I want to use only the images from the database which have some sort of important face features, and maybe not all of the pictures from the database. In other words, I want to blend the idea of PCA and the idea of bases together. If I will convert with PCA my database of 32 images from the previous page into, say, only 4 principal components or images with the 4 highest eigenvalues of the covariance matrix, then I will be able to reconstruct your new image with only 4 numbers. Now, clearly before the application of PCA, I need to convert every image into a long vector just by taking each column and stacking it together. So I will take every vector here, first column, then second column, I will stack it here, then third column, I will stack it here, and I will get very long number, and I can apply PCA to that kind of vector. So I convert basically image to vector using lexicographic order. So if let's say PCA will give me those 4 values, I will use them as eigenfaces. Again, since I'm stacking together all of the columns, they should be aligned very well. It's very important to align well all of the images. Otherwise, this eigenfaces algorithm will not work well. Now, let's see what those 4 pictures are. Technically, I had a database of 32 images, and I converted each one of those into long vector of numbers. So I have 32 long vectors of numbers. Those 32 vectors, I put it in the matrix V and converted that into my space of covariance matrix and found eigenvalues and found eigenvectors of that covariance matrix. Now, since I have 32 images or 32 vectors, my covariance matrix was basically 32 by 32. And from here, I can get vectors, which is from 1 to 32. So I have 32 eigenvalues and 32 eigenvectors. Totally I have basically 32 long vectors from the PCA transform. Now, those sizes of those are different. So I'm sorting them from the largest one to the smallest one. When I'm sorting them, I'm picking only 4 highest values of lambda and picking the corresponding vectors v to those things. Now, those 4 vectors are also very long vectors, but only 4 vectors, which corresponding to the largest lambda values of that matrix. Now, those vectors I can reorganize back to the images because I know the size, the number of columns and number of rows. So I can reorganize those vectors back into image shape. And those are the images that I've got from that. Those 4 images, which are corresponding to the largest eigenvalues in the covariance matrix. Here is one example of a result. Those 4 images are the principal components that I showed on the previous page. Those components are clearly computed offline from the database images. This is a new image that I want to represent using those basis images. So I will call it B1, B2, B3 image, and B4 image. I can find some coefficients in such a way that weighted sum of those base images will be as close as possible to my new image. Now, one way to do that is, for example, using least squares to get minimal error between weighted sum here and the actual pixels that I have here. But after I do that, this is technically the result of weighted sum of those 4 images and not your original image. And you probably even cannot say the difference between your new image that you gave me and this reconstructed image that you see here. Amazing, isn't it? The only problem here, maybe not the only problem, but one of the main problems with that approach is that it is very sensitive to small movements. But this image could be reconstructed only using those 4 numbers. So if you will give me those 4 numbers, I will be able to reconstruct your new image here based on my baseline basis images that I have. And this is the idea of eigenfaces, that you can use only 4 numbers to reconstruct almost any image which looks more or less similarly to your basis images.